So essentially I go to a limit of an infinite street. And I write my partition function in this limit, up, down, right, left, right. With the technique of boundary states, you see in this limit I get some translation variance in the horizontal direction. And so this is something I can write with the boundary state technique I just used in a quite different context. Where VU and VD will implement the boundary condition for the up and down side of the strip. On the other hand, I keep track of these boundary conditions on the vertical sides, which now I move to infinity, but they will still play a role in selecting states which can propagate between the two horizontal boundaries. So I keep track of these images here. Okay, then I perform the analysis again in the Potts model below TC. So I consider this means that I'm going to expand these boundary states in the basis of the bulk theory, which below TC are the kink states again. And this is why, so here I know I have Q degenerate vacuum, and I have the kinks interpolated between them. So this is my structure. And so if I have the fixed boundary condition, VA, so here the spins are fixed to the color A. And so this function contains states which start from A and end with A. So in particular, the first one will be the vacuum itself, A. And then I can put kink states, which in this case need to be kink and the kink, KAB, and then BA to go back to color A. Plus, again, area states, which in my limit of large R will again be sublimit. Notice here I put theta minus theta as a rapidity disk of this particle. This is just to implement the translation variance of the boundary condition in the horizontal direction. I want states with zero total momentum for translation invariance in the horizontal direction. So in a similar way, at this point, I express the free boundary condition. So free here doesn't break the symmetry. So this has been an expansion, actually over all possible states, but symmetrized with respect to the color. So I write this way, sum over cores, then I have a contribution coming from the vacuum. All of them can appear here in a symmetric way. Then I have contribution from single kink. And so on, two kinks and so on. And again, the total momentum in each state has to be zero. So, for example, this single kink, I have to take it at zero momentum, 0, 0. Right. Now, with this, we can go and compute, in particular, this partition function, I use this notation. So this is just a particular partition function which I take A, B, t.
Excuse me.
Yeah.
In the last question, the integral, there is some function there? Since the key has no rapidity there.
If this was theta, there would be some effect of theta.
But why there is an integral then?
Why there is?
An integral.
You're right, sorry. There is just this is G, this is just I reproduced the case of the previous previous exercise of phase separation. In this case, I can figure because the key is to have zero ability to implement the transition plans. Then, so I was saying I'm considering now this partition function, and I use this notation of the indices plus or minus with this meaning. So plus or minus corresponds to t.
Thanks for being here, as you have easily understood.
Yeah. So this plus or minus refer to being above or below PC. So this is, this means P larger or less than PC, which in the language of the Colomo model, if you remember this relation, is T smaller or larger than PC. So there is this inversion going from T to T. So when I put this plus here, this means that I'm actually below TC in the post model. So I'm at the phase in which I have
You don't describe different modes of the system. They're actually only end in the...
So this is why I can write this partition function using these boundary states and the right phase. And of course I'm doing this in the limit and both much larger than 1. But actually ML, like I said, I'm sending it to infinity already, so that we just say that also now is going to be very large. And so I'm using now this expression in the limit I go to infinity, where here the two boundary states correspond to 3 indices. So I use these boundary states. So when I do this, in principle I would have first the contribution coming from the vacuum. But you see the vacuum contribution doesn't match. I'm computing actually 3. According to my notation, this is the partition function. So the horizontal sides, which are the ones I'm associated with the two boundary states here, I have the 3 boundary conditions. So I'm using this expansion. And concerning the vacuum contribution, it cannot be there because the only non-zero term would be 0, 8, 0, 8, but this doesn't match the fact that at plus and minus infinity I have different colors. So the vacuum cannot contribute. The only contribution comes from the king with colors A, B, which match this vertical boundary. So this is why actually here I'm getting a contribution from a single king in which I get a factor of G at each of these vertices. Yeah? So here I have a G square coming from there. Then this propagation factor, I have to evaluate it at the energy of this ink, which is just its mass. So I get here just E to the minus mR, because this has 0 momentum. And then I get the states are okay, so this comes the product of this boundary state with free boundary condition. This is the limit there. Now this, of course, this is trivial. With my normalization, this is 2 pi times the energy or times delta over the momentum. But here is a peculiar kinematic situation in which the particles are both at 0 momentum. So this is actually evaluated at frequency. So here I use the usual volume regularizations for the delta function, and I get here a factor of the mass times the volume, which is L. So I'm regularizing the delta function in this horizontal direction, and I get. So you see, through the delta function regularization, I get back the L dependence that initially I said was very large, but it comes back in this way in the computation. So, putting all together, this is n L G squared e to the minus n. As far as the leading behavior is concerned. Okay, so once we have this, we can this is actually everything we need to infer our results, because now I will involve, without going into the details actually, a duality property of the Potts model that you can see on the lattice to start with. There is a one-to-one correspondence between configurations on the lattice, the original lattice, in which there is some vertical crossing, and configurations on the dual lattice in which there is no horizontal crossing. This is something you can see quite easily. There is a rule, you take the lattice, and then the dual lattice will be this. And if you have an horizontal crossing, say, it will be like. So you can have a configuration like this. Anyway, the rule is that for each configuration of the original lattice, the configuration associated on the dual is that in which you connect the sides on the dual lattice with the rule that you come across a bond which is present on the original lattice. So the corresponding configuration on the dual lattice would be this. Sorry, I should use controllers to make this. And here, sorry, there is no crossing possible. This is not there. So in such a way, you see, if there is a vertical crossing in the original lattice, there cannot be a horizontal crossing on the dual. Okay, so this is. And this correspondence between direct lattice and dual lattice is what you use phase with the low temperature phase. So making the story short, this is why you end up with the conclusion that the probability of vertical crossing below PC coincides with the probability of no horizontal crossing above PC. But now you see that, according to our analysis, this guy here is precisely this partition function I have just computed. Because here, due to the I have A, B, 3, this different color set here forbids horizontal crossing. This is forbidden because I would connect sides with different colors. So this partition function is the probability that there are, when evaluated at q equal 1, so this is q equal 1, sorry, is the probability that there are no horizontal crossing, which is what I'm writing, above PC. So we know the result here. This is, in the limit, is A, M, L, T, minus M. Where A is, we go back here, is G squared, evaluated at q equal 1 in the box model. On the other hand, there is a similar relation in which I exchange the phases. So PD above PC is 1 minus pH below, but this is 1 minus PV below, in which I exchange R with L. So you see, going from horizontal to vertical in the same phase just amounts to swap the rectangle. And then, since I already computed this guy, which was this, I get in the limit, this is 1 minus A and R e to the minus n. I have exchanged the role of R and N. So I got the asymptotic crossing probabilities, vertical crossing probability in both phases. And the result depends on R over xi and L over xi as expected, because n is just inverse of psi. But this n here, we know it is related to the inverse correlation length, which is a measurable quantity, perforation. So everything here is measurable. And explicit, the only thing I didn't specify up to now is this amplitude A, which is universal. And this, well, I have no time to go into any detail of this, but you remember this amplitude was arising from the boundary state. So it was essentially decoupling of the key to the boundary. Now, the game I played in these lectures of scattering theory in the bulk can be repeated in a situation in which you have a wall and then you have a particle going on this wall and bouncing back. So this is the so-called boundary scattering, which to a large extent can be seen as a particular case of the bulk one. Suppose it's like one of the particles in the bulk becomes infinitely massive, so and it is stuck at the origin of your space coordinate. So this will play the role of the boundary, and particles arriving at one definistic will be reflected. So you can, there are integrable cases also for this boundary scripting, and the Potts model with a boundary is with boundary conditions which are free or fixed is one of these solvable cases. So if then you can compute this reflection amplitude, this will be theta minus theta here, so this is something called R of theta, the reflection amplitude for this process. And you will find that this amplitude possesses some poles again that you can interpret. There will be some bound state poles corresponding to the particle being captured by the boundary. But then if you also play with the direct cross channel, you will have also configuration like this. Poles corresponding to situation like this. And so here you have some particle. And so if you read then the residue of such a pole, you will have here a three-particle coupling corresponding to this vertex, which is something you already know from the bulb. Here we are in the bulb, and this is precisely one of the vertices we computed for the bulk spectrum. On the other hand, here you pick up another contribution related to the coupling of the particle to the boundary, and this G is this G. So when you do this in the Potts model, this is a function of Q. You get this number, you go to Q equal 1, and you can find this amplitude exactly. It turns out to be 3 minus square root of 2. And this completes the derivation of these asymptotic crossing probabilities, which are given here in exact form. Right, so this is an application to calculation of boundary states. Again, we have a particular timing, so I'm going to conclude maybe with the last observation related to this, since we are here. So I said more than once that, and this is what people say normally, calculation transition is such that above this critical value PC there is an infinite cluster. Now, something one can ask is that this infinite cluster is unique, or there are several infinite clusters above PC. In any case, how many of them? Yeah. So this is actually something we can answer. Observing that it comes from our expression of the Potts partition function in terms of clusters, that the average number of clusters, call it n1, is given by the derivative with respect to Q of the log of Z. This is interpolation, this is what. Because now I'm taking 3 everywhere, so I don't put any, I don't fix any color on the boundary, and so I get the factor of Q for each cluster in the configuration. So, in this way, I count the total number of clusters taking the derivative of the log. On the other hand, this, if I'm interested in the number of vertically crossing clusters. will have clusters like this, which I call V, and I want to count these clusters. This will be a subset, of course, of the total number, and this subset will be the total number minus, I have to subtract the number of clusters which live completely in the bulk, I call them V, but I also need to subtract the clusters which touch, say, the upper side, and also those which touch the lower side. So, now, an easy exercise which follows from the game I played with these boundary conditions, and you can check it easily, that these combinations of cluster numbers can be written in this way: derivative with respect to Q of the log of Z33 Z8 So if you go and look in each case, you will see that when you put all together, you get this combination. And of course, for calculation, I take everything into account. Now, next observation here is that all these partition functions, except the first one, involve, so they have, for the horizontal sides, at least one is fixed boundary condition. So this means that you remember the expansion of the boundary state with fixed boundary condition is the one which contained the vacuum and then kink anti-kink. So there was no single kink contribution. I'm finished. So this means the vacuum will contribute some constant, which at the end, so is constant plus some dependence on R, which are what we are tracking. And so all these partition functions, except the first, are in the form constant plus order e to the minus 2 mr. A large mr because I pick up here the two kink states. Only the first one is of the form constant plus order e to the minus mr because it contributes a single kink. This means that in all this expression, when I go to mr large, the first partition function is the one which gives the leading contribution. And this is, so this becomes the Q of log of Z. Yes. And this, if you remember now, the expansion of this free boundary state will be the Q log of Q. I get the factor of Q coming from sum over floor over the vacuum. This is the vacuum contribution, I get the factor of Q. And then from the kinks, I have sum over A different from B of this contribution of kink type A. And this produces Q times Q minus 1. And then I know if the rest of the expression Okay, so this is the option. You take the derivative and you find, and if you take everything then x equals 1, and this is 1 plus and equals because all the rest are things we already computed. A is this amplitude. And you see that then in the limit r going to infinity, when we are in the limit of the infinite plane, we are left with a single infinite cluster. There is a single cluster which is able to span through the Wood system, which in the limit r going to infinity becomes the Wood plane. So, when we say interpolation, there is an infinite cluster above PC, it is actually just one. And so this was the last exercise I want to mention. And we are quite late, and I'll stop here. Thank you for the attention.
We shall recover time. We have time to recover time for lecture by other people, so we can take a bit of time. If there are questions, please feel free to ask, and if you have some final comment, please feel free to add as well.
No, I think I can stop here and defer further discussions to the discussion section of the afternoon and prior discussions until the end of the week. So, unless you have questions right now, I will stop.
Just a short comment. So in this limit, we are finding that n bar is equal to n v bar. So at the end, all the other contributions are not counting.
Yeah, essentially this is.
Okay.
Other questions? So thank you again, and sorry for everything.